These notes are an introduction on how to create graphs for your biology class. To start, there's different kinds of situations in which you would be collecting data in biology, and eventually you might be presenting this data in a graph. Going back to the data collection, perhaps you might be tracking temperature changes in a prairie in Illinois over the course of 1 year. So maybe you take the temperature each day, average the temperature over the course of a month, and then track that average temperature for the year. Another example is maybe you're actually conducting a well-designed experiment and you want to see how fertilizer will produce the most growth of a plant. And so you apply fertilizer in various concentrations. And then you measure how much the plant grows over time. Once you've been involved in some sort of data collection, what you might want to do next is graph it. Graphs represent data visually. They are often more easily seen and understood by the viewer than just presenting raw data. There are many different kinds of graphs, but typically you would see one of the 3 following graphs in science class. The first is a line graph. The second is a bar graph. And the third is a pie chart. Starting with a line graph is used to track changes over time. They usually are usually used to show some sort of progression or trend in data. Line graphs can also be used to compare changes over the same period of time for more than one group. So for example, in this graph over here, we have age and we have height. So as Russell ages, what is his height every 3 years? The progression is his age. And then what depends on his age is his height. Now, aside from time, you might also just have a progression of what's being manipulated. So in our fertilizer experiment, you are manipulating the amount of fertilizer, and more than likely you're increasing the amount of fertilizer. So that would also be a progression. Now, moving on to a bar graph is used to compare things between different groups. And usually those groups are unique and don't have any role with each other or influence on each other. So for example, what I've shown you over here is the world's 10 largest cities and the population in millions of people, and you've got Tokyo, Jakarta, Delhi. You wouldn't put this in a line graph because one data point wouldn't have anything to do with the next data point. So it wouldn't make sense to have a line graph, but a bar graph makes sense because each of these cities on the x-axis is an individual thing that does not have any influence on the next. Finally, a pie chart is best used when you are trying to compare parts of a whole. They do not show changes over time. So the example shown here is if the entire pie is all of the biomes on Earth, each individual slice is what percent are the various biomes. So mountainous biomes or tropical rainforest. So this is useful when you're trying to explain parts to a whole of something. Now, any good graph needs to have the following things. First of all, it needs to have a descriptive title. And the title will have a short explanation of what is in the graph. For example, states with the most elementary and secondary schools, going back to the ones that we had, the one that we had higher, Russell's height at a 3-year interval. And typically you're going to be mentioning both the X and the Y axis in your title. You also might have a color key or legend. So notice that the biomes have a legend on the right-hand side, so you know which color is what. I would also even argue that even a line graph probably should be in color, and if you have more than one graph on the page, then you would need to have a legend to show what color means what. The next one is really important. You need to have a consistent scale for both the X and the Y axis. For example, if given years for the X axis, they must be spaced out with a consistent scale, either every year, every 5 years, etc. So you would want to go 0, 5, 10, 15, 20, 25, 30. I can't tell you how many students are not consistent with scale. And if you have an inconsistent scale, it totally throws off what the graph looks like and what it's trying to show. Your graph needs to have an X and a Y axis, starting with the Y. The Y axis has numbers for the data that is being collected. This axis represents your dependent variable. Remember, D for data. The x-axis runs horizontally. Typically, the x-axis has numbers representing different time periods or the names of things being compared if it was a bar graph. This axis represents your independent variable. So, x-axis, y-axis. So, if we're taking it from the top and you are about to make a graph, first, craft a descriptive title and write that title at the top. Determine what's the x-axis and what's the y-axis, and label them as such. So for example, in the graph down below, the x-axis is hours of sunlight. Notice it's time. So you would write hours of sunlight. And then the y-axis is the height of the plant. So you would label height of plant in centimeters. The x-axis is our independent variable. The y-axis is always going to be our dependent variable. Determine an appropriate scale for each axis. For example, you might decide that one space on the y-axis represents 1 millimeter of growth, and one space on the x-axis represents 2 ounces of fertilizer. No matter what, your scale must be consistent and allow for all data points to fit on the graph. It's never fun to come up with a scale only to find that the next data point either falls off the end of the X or is too high for what you've put as a scale on the Y. And then you have to erase everything and start over. So it's best to figure out the scale in advance so that you know once you've plotted all the data points, they're going to fit on your graph. If required, use color for your graph and include a legend or a key so the reader knows what each color represents. Finally, plot your points by looking at the X value, moving over until you find that value on your scale, and then moving up and moving up until you find that value on your scale. So essentially it's over and up. So we're going to practice together. Here's a problem, and actually it's two graphs, but I'll come back to that in a second. So let's read the prompt together. The thickness of the annual rings of a tree indicate what type of environmental situation was occurring at the time of its development. A thin ring usually indicates a stressful period of development, lack of water, forest fires, or a major insect infestation. On the other hand, a thick ring indicates optimal growing conditions and reduced stress. Graph the following two forests, comparing the age with the average thickness of the tree rings in Forest A versus Forest B. Use two colors to represent each forest. So first of all, we're going to say that Forest A is red. So here's my key or my legend. And we'll make Forest B blue. And we can start off with a descriptive title. So average thickness of annual rings, and that's in centimeters, versus age of tree in years. So we have a title. Now we have to come up with a consistent scale for our X and our Y axis. So here's the x-axis, and this is going to be age. And we have to get up to 60, but just eyeballing this, I don't think that there's 60 individual little blocks here. So I don't think I want to go by ones, but I bet you there's 30 blocks here. So I'm going to go by twos, and let's just see if it works. So 2, 4, 6, 8, 10. I'm not going to label them all. I'm just going to show you what I'm doing. 2, 4, 6, 8, 20. 2, 4, 6, 8, 30. 2, 4, 6, 8, 40. 6, 8, 50. And look at that. Now, we didn't use toward the end. However, it looks like we made the most of our space. So that's good enough. And then the thickness, the highest number is 4.5 on both graphs. So we have a lot of boxes to work with here. So if we, let's say, go by 0.2, 0.2, 0.4, 0.6, 0.8, 1, 2, 3, 4, 5. That fills up most of our space. So now we're ready to graph our data. And I'm going to go back to red. We're now just graphing Forest A. You can ignore Forest B for now. We are going to go, and this is X and this is Y. So we need to go over and then up. Over to 10 and then up to 2. So there's our first data point. Over to 20 and up to 2.2. So I'm going to zoom in a little bit more here. So over to 20, up to 2.2. Over to 30, up to 3.5. So over to 30, up to 3.2.4.5. 40 is 3. 50 is 4.5. If you zoom in a little bit, so there's 50, 4.5. And then finally 60 is 4.3. Now, depending upon what your teacher or lab is asking you to do, you might just draw a line to connect your data points. And you would be doing this much neater than me. Or you might have to draw a trend line. For what's being shown here, I'm just going to connect the data points. Then you'd want to graph Forest B. And so we'd have to change colors and graph the second forest using the same scale and the same graph paper. So age 10, 2.2. Age 20, 2.5. Age 30, 3.6. Age 40, 3.8. Age 50, 4.0. And age 60, 4.5. Now, what this graph is showing me is that overall, Forest B seems to have more favorable growing conditions than Forest A. There was a period of time where that was not true, but for the most part, here, and it's starting to look like here, Forest B had less stressful conditions than Forest A. So that's your example. Just to recap, x-axis, independent variable, y-axis, which I forgot to label, so it's a good thing I went back and I checked. This is average thickness. Of annual rings in centimeters. We have a title, we have a color key, and we have 2 line graphs. Thanks for